Hello everyone. This next lesson is on supersaturated solutions and solubility curves. So we'll begin with supersaturated solutions. Not too much to go over here, just another kind of a solution as an extension to what you probably did in grade 9 and 10. All right, let's start. So a supersaturated solution is essentially one that there is more solution dissolved than could actually exist. Now, how can you manage that? I'll explain how in just a bit, but essentially an unsaturated solution means that more solute can be dissolved. A saturated solution is really the point where no more solute can be added. Right? Then a supersaturated solution can really simply just be that you've added so much solute that it begins to crystallize at the bottom. And maybe we actually did this properly in class from not realizing that it was going to be useful, at least in this way. But we created crystals in class, and that's essentially created a supersaturated solution and allowed it to simply dry. And we had some crystals made. Some looked better than others. Would have loved to have continued that, but it's okay. At least you got to see a supersaturated solution in action, right? Okay, so moving on. Now this is normally the point where I would have that supersaturation demonstration in class, so I have it would look really cool. It's also called warm ice, right? I'm sure if you type that into YouTube, you'll find some cool videos. We would have done that in class. Okay, so how do we make a supersaturated solution? That warm ice example was made, or can be made, like this. So what you'll do is I'd like to think of it as tricking the solution to thinking that it can hold more than it will be able to. So a supersaturated solution, or water essentially, is heated, and then so the solvent is heated, and you slowly dissolve solute into it until you reach until it becomes saturated. Right, so you slowly dissolve, highlight some key points here, take a highlighter out. Right, so you heat your solvent. You heat your solvent, usually going to be water. Right, and then you slowly dissolve solute until it becomes saturated. Then you let it cool. So you've tricked the solution into holding a certain amount of solute at a certain temperature. Then if you let it slowly cool, it still remains dissolved. But what can really happen at that point, once it's cooled enough, is it can crystallize rather quickly, rather impressively. So by disturbing it, by adding a seed crystal to it, right, seed crystal, by adding a seed crystal, or by a sudden disturbance like a scratch, just simply scratching the outside of a flask or the container that it's in, with even your fingernail or a glass stirring rod, could be enough to make the solution, make the solute come out of solution, and you get that quickly forming crystal. That looks really cool in this demonstration. Okay, now that's essentially it for supersaturated solutions. Now a solubility curve, which is certainly related to that, is what we're going to do next. We would go into a gizmo simulation here, and we will use explorelearning.com. But for now, I'll just show you what the results look like. So in the simulation in explorelearning.com, you perform a virtual lab, which would yield certain results. I already have this Excel file open, and it looks like this. So it's not a proper graph. I'll label the axes, but before we do that, here you can see that we have a certain mass in grams of potassium nitrate. Oh, it's writing for me. That's excellent. Can you erase that? Let's practice that. Okay, so here we have a certain mass of potassium nitrate. So 17 is all in grams. And we have temperature all in degrees Celsius. Now, what we see here is that as you increase temperature, so from 5 degrees Celsius, 10, 15, 20, we're able to dissolve more and more solute, more and more potassium nitrate, so that you end up with, let's choose that one, see what happens there. You end up with a graph. So if we plot this very simply, again, the graph isn't made well. We're missing axis titles here and title for the graph and all, but you get this line, this curve, not a line, a curve. You get a curve that shows you the relationship between temperature and mass. So we can say that as you increase temperature, you therefore also increase the amount of solute that is able to be dissolved in solvent. And this is essentially a solubility curve. Okay, I'm going to go back to our lesson here. Okay, so that same solubility curve, all I did here is just took a screenshot of it. I labeled it properly. So this is a solubility curve. Probably should have written solubility curve for, I think it was potassium nitrate. Yes, for potassium nitrate. Okay, mass of solute in grams would be your y-axis. And temperature, I should write temperature in degrees Celsius. Let's see if I can modify that, because it's temperature in degrees Celsius. I don't have that symbol ready to go, but degrees Celsius. We'll just write that for now. Okay, so along this line is where you've reached saturation. So you can read this graph and say at, say, 20 degrees, sorry, I'm pointing to 10, I'm saying 20. At 10 degrees, you can dissolve about 20 grams of solute, and that's going to be saturated. At 20 degrees, you can dissolve about 30 grams of solute, and that's said to be saturated. Right? You can also say at 40 degrees, approximately 60 grams of solute can be dissolved, and that's going to be a saturated solution. Anything below that line, below this curve, is going to be unsaturated. So you can say that at 20 degrees, if we dissolve 10 grams of solute, then that's going to be an unsaturated solution. Whereas anything, let's say at 30 degrees, anything beyond this line, so to the left of the line, let's say 50 grams at 30 degrees Celsius, at 30 degrees Celsius, so roughly at this point, right, roughly at that point, that is going to be a supersaturated solution. Right, so this is a typical solubility curve, in this case for potassium nitrate, but you will always have these two areas. Along the line it's a saturation or saturated solution, above that line is a supersaturated solution, below that is an unsaturated one. Right, and that's how it looks, how it properly looks here. Right, a solution or a substance is said to be soluble if at 10 grams you are able to dissolve 1 liter of it. So that's typically what the consensus is. And the solubility of a substance is just the amount that it's able to dissolve at, of course, a certain temperature. Okay, it's hard to see this. There is a curve here in this direction. I'll draw it out a bit better. Let's let's use red. Red is good. Okay, so I can follow that line properly. So far, so good. Looks like this. So here's where we would normally stop the class and say, what is this? What does this mean? What does this tell us? So think about what this tells us. Here we have the same axes, so mass in grams along the y-axis, along the x-axis we have temperature in degrees Celsius. So normally we would have had a line that looks a bit different. It would go, let's just draw it. Normally we may have had a line that looks like this, roughly, right? I'll undo that. That's not what we have here. Here we have a line that goes in this direction. Now, you should be looking at that and saying, as you increase temperature, it looks like you can dissolve less and less. The other thing to point out is that this isn't a solid, this is oxygen gas. So the solubility of gases, they tend to decrease as temperature increases. Now that's typical among most gases. There are likely exceptions, right? But essentially this is the general rule. The solubility of a gas will decrease as you increase temperature. That can be, you may have observed that if you maybe have left a carbonated soda out in the sun in the summer, and you go back to it and it's gone flat. Well, it's gone flat a lot faster than it would normally because you have increased temperature and therefore decreased solubility. Okay, no need really to have to know this or know details about this, but just to make an environmental connection here. Many factories use water as a coolant. Now that water may not come into contact with any kind of substance, it may not become polluted, say, but it's used as a coolant to cool off any kind of process that happens in a plant or in industry. Now, if this water isn't polluted or dirtied, and if it's put back into a lake, a river, or body of water, it would be put back at a higher temperature. Now, think about why that could be dangerous. Right? This is often a communication question on tests. Then I would normally have you watch this video. Now, in our Google class, I've posted a link to this video. Give it a watch. It shows what the effects. It talks about what the effects of increasing temperature and climate change have on cooler environments. This is a pretty good solubility curve of, well, not just one, it's of many. We get potassium iodide here, sodium nitrate, that potassium nitrate curve we talked about right here. Ammonia over there has a different relationship there, potassium chlorate. So lots of solubility curves here. What you'll need to make sure that you understand to do is just how to read these curves. At what certain temperatures for a certain line can you dissolve to reach a saturation point, or an unsaturated point, or something that is supersaturated. And here is your work. Right, you have two parts here. Something that is in your textbook, some great background in your textbook, and then a solubility curve worksheet as well that is also posted online. That is it for this lesson. I'll see you next time.